Hello, my name is Pablo Ravazzoli and I'm going to present the work titled Gravity Effects in the Retraction of Liquid Filaments Resting on an Inclined Plane. This work was done with Drs. Alejandro González and Javier Diez. This talk is going to be presented in 5 sections. In each one, I will describe the main aspects that allow us to compare the experimental results with the numerical simulation ones. We are concerned with the retraction and fragmentation of a long liquid filament sitting on an inclined substrate under partial wetting conditions. In order to create the filaments, we fill a vessel with the silicone oil and we generate a shed that flows out of the vessel bottom. Then, with the controlling impact of the substrate against the shed, we obtain the thread with uniform width and parallel straight contact lines. After that, we place the substrate with the filament over an inclined base with the axis of the filament along the gravity component parallel to the plane. As we can see in the scheme, we will focus on the retraction of each extreme, where the uphill extreme recedes in favor of gravity and the downhill do it against gravity. The process also implies an advance of the contact line in the transverse direction. Experimentally, we place the substrate with the filament over a commercial goniometer mounted on a tilting base. This allows us to capture what happened at the extremes, one at a time. Now I'm going to show you 2 videos, one for the uphill and the other for the downhill extreme. As it happened for horizontal filaments, the end of the filament starts to recede along the longitudinal direction. This produces that a bulged region is formed. We refer to it as a head. The process generates a thinner region between the head and the rest of the filament. Call it neck. Here we can see the head and the neck. The neck region rapidly breaks up, leaving a sessile drop separate from the filament. Now we are going to see the difference between the retraction distances for the uphill and downhill extremes. In the figure, we can see the tip position for the horizontal case in black dots, and also the tip position for the uphill and downhill extremes in red and blue dots. In the horizontal case, the both extremes of the filament recedes in the same way. For the inclined case, the downhill tip, the blue one, recedes a shorter distance than the horizontal case, and it do it with a smaller velocity. For the uphill tip, the red dots, recedes a larger distance than the horizontal case, and it do it with a faster velocity. The gravity effects are not important for early times, for the first 20 seconds, but become significant for later ones. Now, I'm going to show you the high profiles difference between the horizontal case and the both inclined ones. At the initial moment, the 3 profiles are coincident. At the middle time of the whole evolution, it can be seen that the downhill retraction, the blue profile, is shorter than the horizontal case, the black profile, while the downhill profile is larger, the red profile. In all the cases, we can see the initial state of the neck formation behind the head. At larger times, near to the breakup, the tip of each extreme is practically stopped and the difference between the retraction distances become more significant. Moreover, now it can be observed that the 3 profiles have a different neck shape. Unfortunately, For the uphill case, the neck region is out of our visual field. After the complete evolution of the filament into an arrangement of drops, we measure the space between them. This distance is equivalent to the total tip retraction. As expected, the separation for the uphill drops is larger than the horizontal case, while the separation for the downhill drops is shorter than the horizontal case. In Table 1, I present the typical values of the dewetted length obtained for each case. This gives us the idea that the alpha variation could be used as a method to control the final distance between drops. We want to construct a hydrodynamic model in order to perform numerical simulations of the Navier-Stokes equations. For that, we need a boundary condition that correctly models how the liquid wets the substrate. This model is the consequence of a combination of a hydrodynamic one, the Cox-Boinov model, with a molecular one, the Blake model. The result of this is the Cox-Boinov plus Blake model, first proposed by Petrov. This model gives us the following relation between the contact angle theta with the velocity of the contact line. The macroscopic length scales is the capillary length, here equal to 1.45 mm. The microscopic equilibrium contact angle is theta 0. Also, the model has another three parameters: the microscopic length scale L, the characteristic velocity v sub 0, and the dimensionless parameter gamma. These three parameters are from molecular origin and depend on both the frequency of molecular displacements at equilibrium and the average distance between adsorption sites. These values were previously reported on the same liquid and substrate used here, but with the drop configuration method. The wettability models usually relates the contact angle with the velocity of the contact line, so that we measure this relation for the tips of the three static cases, the dots in the figure, and compare them with the Cox-Boinov Blake model, the grid solid line. We can see in the figure the good agreement between the model and the experiments. Now, we use this wettability model as the contact line boundary condition in the numerical simulations. For that, we numerically solve the dimensionless Navier-Stokes equation with the moving mesh method. In the figure, we show the top view of the filament evolution, a visualization that is not possible to be obtained experimentally. The general picture of the process is similar to the observed in the experiments. The downhill extreme resists less distance than the uphill one. Unfortunately, the numerical method does not allow a separation of the fluid into several domains, so we are not able to observe the breakup process. When we compare the numerical tip position for the different cases with the experiments, we observe that the numerical simulation underestimates the displacement for the horizontal case. This is shown with the solid black line. This phenomenon changes when the substrate is inclined. For the uphill stream, the red dashed line, the difference between experiment and simulation increases, while for the downhill extreme, blue dotted line, this difference decreases, becoming practically negligible. In order to show the shape difference between the experimental and the numerical height profiles, we shift The experimental ones still make coincident the tip position of the contact line. It can be seen for the time equal to 50 seconds, and more relevant for later times, that the main shape difference is in the neck region. The numerical profile is not sharp enough here and here, and we believe that the slower retraction of the tip could be associated to the fact that the numerical model do not break up. Arriving to the end of the talk, I want to summarize the obtained results. The presence of the longitudinal component of gravity modifies the distance between drops. There are characteristic the wetting retraction distances for the uphill and downhill process. Numerical simulations reproduce the main features observed in the experiment. Nevertheless, the lower velocities produce a time delay in the evolution. A complete understanding of this phenomenon would allow to develop a control method in order to produce an array of self-positioning drops with varying space. Thank you very much, and feel free to write me if you have any questions. Goodbye.